to the sixth edition of our annual webinar from the European Federation of Corrosion's Working Party 4 on nuclear corrosion. We do this a bit as an appetizer also to the EuroCore, and because we don't have an event usually during the year except the EuroCore at this year especially. So, but before we start, just would like to remind you that you find quite some information on the website of our working party, on the EFC website. So you see here a link, and if you scan the left QR code, you can get to this website of our working party. And then, also not too long after the summer break, there will be EuroCore coming up in Stavanger, Norway, from September 7 to 11. You can still register, of course, not talks anymore, but attendance. We'll have a very interesting nuclear corrosion session lasting almost 3 days with, at the moment, 38 talks and 5 posters. This can slightly change, but roughly it will be. You see the website to the EuroCore with the right QR code. And finally, there's a little or short summer school just before EuroCore in Stavanger at the University of Stavanger with a very interesting topic, and you can still register if you want. The link is also on the EuroCore 2025 website. The very final registration deadline for this school is July 18. So please, it's very nice. It's 2 days, Thursday, Friday, and a little bit a social event on Saturday, and then Sunday EuroCore starts. So it's a good opportunity. So, and now we are at 21, so I think it's time to start with our actual webinar. So welcome again for those who still joined. This year we have a very interesting topic as usually, and the title of our talk is called Accelerated Alloy Discovery for Molten Salt Reactors via High-Throughput Corrosion Testing and Machine Learning. And it will be presented by Adrien Couet, who's at the moment a professor in the Department of Nuclear Energy and Engineering, sorry, it's a bit hot here, Engineering and Engineering Physics at the University of Wisconsin-Madison, where he managed the materials degradation under corrosion and radiation laboratory. He has a PhD in nuclear and mechanical engineering from Penn State University, where he focused on corrosion of nuclear fuel claddings, and currently is working on the fundamental understanding of materials degradation in extreme environments with a focus on light water and molten salt reactors using state-of-the-art characterization techniques and first principle modeling. And lately he started with alloy design based on high throughput experimentation and machine learning based modeling. And I guess this is also where the talk now will focus on. So I stop sharing and then the floor would be yours. One comment, please, if you have questions and comments already during the presentation, you can enter them in this Q&A tool. Or if that would not work, then you can, of course, also enter it in the chat. And the talk will take roughly 45 minutes. And afterwards, we would have plenty of time for questions and discussion. And I can also, if it's too complicated, you can also finally, after the talk, raise your hand. And then I think I can allow the microphone, open the microphone for you, and then you can also orally present your question. So now,
all right. Thank you very much, Stefan, for the very nice introduction. Hopefully you can see my slide.
Yeah, it looks great.
Okay, perfect. I will just do the pointer. Here we go. Yeah. So thanks, Stefan, for the very nice introduction and for the invitation to present at this seminar. It's always, even though I'm in the US, I'm always very enthusiastic about presenting my research to the European members. And so today, it's a work that involves a lot of people. So I have a chance to present this, but there is many people, especially in my group, that have worked up over the past 5 years, 5, 6, 7 years on this topic. The most influential people in terms of work that I'm going to show today are in bold here. Many of them have graduated. Other people are here, either graduate students or postdoc in the group to work on that. And then there is, a series of collaborators that have helped with molten salts in general within my research group. And I wanted to highlight many of them here. You have, a ton of sponsors and funding agencies that have made this possible and are, they also keep giving us funds to keep working on this. And then the materials degradation and the corrosion and radiation lab, which is this MatCore lab that I manage at UW-Madison. So since it's not a nuclear, necessarily very, very centric crowd, right? We're here to talk about corrosion. I always like to do a little speech about nuclear first, why I think nuclear energy is important to our world, and why I wake up in the morning going to work. Basically, that's the bottom line of this. So I'll just show a few slides on that, and then I'll move on the nuclear materials more specifically. But just so you know, this is a very recent graph that was put together by the International Energy Agency that shows all the emission per sector in the world globally, and there are a few things that are interesting to see in this plot. First of all, this is from the stated policy scenario that's called STEPS. This STEPS is basically means that if every government is actually doing what they say they would do in terms of policies, like this plan for 2040, 2050, and so on, this is what it's going to look like. Needless to say, this is very optimistic. You see how the world is moving right now, especially in the US, right? We are probably, we're coming back on many of those policies. So I would say what you're going to see right here is an optimistic scenario, which means, so that scenario is basically the CO2 emissions are kind of plateauing a little bit up to 2050. So that's the first interesting aspect. The second one that is important is to know that electricity production is the main producer of CO2 in the world right now. And so if we can decarbonize electricity, this is very important. But then, of course, you see that there is industry and transport as well. And so if you can electrify the industry and you can electrify transport, your impact on the CO2 emission is multiplied, right? So really, decarbonizing electricity is one, if not the major key driver toward a reduction of the CO2 emission. So with this, the problem, though, is that if you look at the electricity production in the world today, it does not seem to follow a decarbonization trend. Clearly, the plans, again, this is an IEA report, it's a little older. This one is 2018, so it was right before COVID. But honestly, this has not changed a lot. You have, the main production means for electricity are CO2-based CO2 emission-based production means. So you have coal, oil, and gas. Only a small section is for nuclear and renewables. So clearly, the trend is not to the decarbonization of electricity production, and that's a problem because if you look at two plots, they have the same units here in terms of billion tons of CO2 emission that are per year, and you see that this is a well-known report from the United Nations in 2018 about global warming. That's at least in the US, people realize that this was looking not very good. That if you want to keep the temperature rise below 1.5 degrees Celsius, this is a trend of CO2 emission that you have to follow. And one can notice that you have to be even negative emission. So that means you have to capture carbon in the atmosphere. So clearly, those two plots are not going very well together. That's a bit of one of the conundrum of our century is how can we actually make this work, right? Well, I do think nuclear is one of the solution, or part of the solution, I would say. And here is an interesting image where you see Europe electricity consumption it was July 1st, so 2 days ago at 6 p.m. In Europe. And this shows you the carbon intensity. Well, I don't know where you're from in Europe, but you can pick your country, take a look. This is this website here at the bottom. It's a very interesting website. I really encourage you to look at it. But if you go a little closely and you look at France, for instance, France, as you know, has a strong nuclear capacity. So at 6 p.m. on July 1st, it was using almost 3/4 of its capacity. Oh, sorry, 2/3 of its capacity, about 40 gigawatt, a bit of solar, a bit of hydro. And at the end of the day, the carbon intensity is extremely low. 93% is low carbon. So that's a pretty good picture, right? For if you want to decarbonize electricity. The neighbor Germany at the same time, as there is no more nuclear in Germany. They have a significant capacity of solar. They have 100 gigawatt solar. They have an extraordinary capacity in wind of 70 gigawatt. But at 6 p.m. That day, I don't know, maybe the sun was already setting or something like that. But clearly, not much of that capacity is being used. And so the coal and gas have to come up to take their part here, which is why the carbon intensity is about an order of magnitude higher in Germany than it is in France. And if you move a little bit further to the right or to the east to Poland, and that's clearly an even more dire picture, where you see in Poland the carbon intensity is about double the one in Germany. The solar and the wind, again, probably the same weather than in Germany at this time. It was not very much used, and most of it comes from coal and gas. So, as a professor, I like to put grades, and that's more or less the grades of CO2 production for the different countries, for some different countries in Europe. So, how can we decarbonize electricity production, right? So as I showed, nuclear is one of the paths, is one of the really important means to do this. And so if you look at the US over the past 10 years approximately, this is a 2015 picture, right? That was taken from Third Way, which is a bipartisan lobby in Washington DC, and you see that we have an interest in using light water reactors. Those are going to be used for many, many years, many decades. We're going to build new ones, whether it's in France, in the US, or so on. New ones are being built and will be built because we know how that works. We know how to make them relatively efficient. We have lots of experimental knowledge about those, right? But they're also very expensive, and they may not be the fit to every single countries in the world. And so, small modular reactor are mean for they're about 50 megawatt or so, 70 megawatt, and so those can help maybe smaller communities, smaller countries, or they can also help industry like mining industry or so on to actually get energy on site, rather than relying on diesel generators and so on. And then, of course, there are those advanced reactors that we probably have heard for many, many years by now, which are a little more than paper reactors today, thankfully. There are many companies and startups that are looking into those. And while clearly this is not going to happen before 2030, there has been significant advancement globally on the design and development of those advanced nuclear reactor. Just to give you just a fresh news, right? As early as yesterday, President Trump, said that by about 9 months from now, INL, Idaho National Laboratory, they have what's called a dome reactor. So this is a former dome of EBR2, which is a liquid sodium reactor that they used to have in the 80s. And for research, they kept the dome, and in this dome, they're going to actually put micro reactors running in 9 months from now. And two were selected for this. So really, this is we're not there yet, but I think we've never been as close in terms of commercialization of advanced nuclear technologies. All right, so let's take a look at the materials now, right? Materials, as you probably know, if you're here, are one of the main limitation to the development of those advanced nuclear technologies. This is a well-known plot here that you may have seen many times, where this has been published in 2009, where you have the temperature on your left-hand side and the DPA. So DPA is displacement damage. It's a mean to quantify irradiation damage in materials. So if you look at 1 DPA, which seems relatively low on this scale, 1 DPA means that every single atom in your material has moved on average 1 time from the lattice site, which is a lot when you think about it. If that really happens, then just the material vaporizes and is blasted. There is just nothing left. So thankfully, this is not what's happening in a reactor, because most of those defects that you create, most of these atoms that have been displaced, they are going back to their original site or to a similar site very quickly, so the defects are not they don't have a very long exposure, a very long lifetime, right? So thanks to this recombination of defects, you don't form a lot of defects, and you don't vaporize your material just with 1 dPa. So this plot here, you may recognize some acronyms. We are here interested in the molten salt reactor right there. But interestingly, you don't see corrosion in this plot. Well, that's because only 10 years later, the same group of people kind of realized that, okay, corrosion is actually another aspect, not only temperature and irradiation damage, but corrosion is another aspect that limits the deployment of materials for reactors. And if you look at this relative corrosion susceptibility, it's very qualitative, huh? But you realize that the molten salt reactor, in addition to the lead-fast reactor, are the two reactors that have the most detrimental type of corrosion degradation out there. So really, if you want to develop a lead-fast reactor or molten salt reactor, you have to think about corrosion very, very seriously. And I always like to show that even though those were people that those people that developed those plots or those graphs were professors at different universities, there is also people that are out there, very big picture, like Bill Gates, for instance, that actually is also aware that material science is one, if not the most important challenge for advanced nuclear technologies. Here is an MIT Q&A. It's a little old, but Bill Gates is still co-leading these TerraPower companies that he helped fund a while ago, and they're developing advanced nuclear technologies over there. And yeah, material science is one of the largest problems, according to him. All right, so let's take a look at the molten salt, right? A little bit more closely on how materials corrode in molten salt. Well, it's a thermodynamic process first. So you need some driving force for this to happen. So for the driving for the corrosion to happen, you need basically to look at two main, I would say, physical quantities. One is the partial pressure of your allied salt. So those are fluorine or chlorine. So I put X here just to, it could be fluorine or chlorine, doesn't really matter. And if this partial pressure of fluorine or chlorine in your salt is larger than the free energy of formation of your metal chloride or your metal fluoride by a few tens of kilojoule per mole, then you will have this driving force that will lead to corrosion of your material. So how that happens usually is that you're gonna have those ions in the salt that are going to react with your material to form those metal chloride, and those since they're now dissolving in the alloy, you're going to form vacancies at the interface. Those vacancies can disappear by either surface roughness, so you increase the surface area and the energy of the surface of your material, or you inject vacancies. And if you inject vacancies in the material, then that means you have chemical transport, right? The vacancies are going to diffuse via atoms, right? And those atoms are going to also diffuse then on the opposite direction of the vacancies, and you're going to end up with a depletion profile of your alloying element M in your system. So yeah, I like to say that material scientists, they tend to focus a lot on the metal chloride or metal fluoride formation energy because it's the metal, right? The chemists, they focus a lot on the partial pressure and activities of species in the salt. But if you want to work in molten salt corrosion and in many fields in corrosion, actually, you need really to understand both the material science and the chemistry. And that's, usually the field of electrochemistry, because that's the field of the interface often between materials and environment. And it's one that is a little challenging to really fully grasp. Just as a side note, why it's a complex field to work on is because the material scientists and the chemists, they followed different paths for many years. They have developed completely different, standards and so on. And sometimes it's a little, tricky to get back from one to the other, right? So one of the aspects, for instance, which is more material sciencey, to look at corrosion is to use Ellingham diagram. So you have Ellingham diagram on the right-hand side here. This shows the free energy of formation of some compounds in salt as function of temperature. So here is for the fluoride. the lower the compound is in this plot, the stable it is. So you're going to have a lot of very stable salts, barium fluoride, lithium fluoride, sodium fluoride. Those are very stable. And then you have less and less stable elements that are out there. So for instance, molybdenum, and if you were to keep up like this gold and so on, will be very unstable fluoride. They would prefer to remain metallic. So the important part here is to have your partial pressure of fluorine that is basically lower than a line here of an element. If that is the case, then it means the salt is reducing enough that it's not going to actually lead to the corrosion of this specific element. So how do you control that? Well, one way to control the partial pressure of fluorine or chlorine in your salt, in this case, is to use, well, for the fluorine case, we use, for instance, a beryllium rod. You see that beryllium fluoride is extremely stable. So beryllium is going to be in equilibrium with beryllium fluoride, and so you're going to bring the redox potential of your salt very low. So it's basically an insoluble, soluble type of redox buffer. And if you look at FLIBE salt, then the partial pressure of fluorine will be about here, and aluminum, titanium, manganese, all of these are going to be stable in the salts. So those are the best salt, right? But it's kind of difficult to do that in a real reactor because you need to put beryllium metal a little everywhere, and that's not the best, of course, both for toxicity and for salt thermophysical properties. So another way that people have found for many years now is that we are putting fuel in our salt, so we have uranium. Why don't we play on this this amphoteric approach of uranium where you have different oxidation state of elements like UF3, UF4, and if we control this ratio, if you control this ratio, then you control the partial pressure of fluorine. So that seems a very powerful mean to actually control partial pressure. If you're familiar with the molten salt reactor experiment, this is this golden, experiment kind of thing, milestone that was achieved at Oak Ridge National Lab back in the 70s. Out there, they were using a ratio that was relatively reducing. And they were, if you put that in thermodynamics, then, manganese is not, maybe manganese is going to dissolve, but not much. And chromium is stable and so on. So that's a very powerful mean. That's a soluble redox buffer. And another way to do it, although it's not very much used in real applications, is to control the partial pressure of your gases in the overhead gas. And if you do so, then you can control the partial pressure of fluorine in the gas in equilibrium with the partial pressure of fluorine in the salt. You will achieve, again, a redox condition. So if you control the HFH2 ratio in your overhead gas, then you may, you decide where you want this point to be, and you can be more or less oxidizing. All right, so that's cool, but not very much. Because actually, that would be way too easy, right? To do this, controlling this redox buffer is extremely complicated. If you're familiar with PWR corrosion or LWR corrosion, there are very strict redox potential of water in terms of boundaries. We inject hydrogen gas to very strict level to control that redox. And even so, we have corrosion issues in the core of reactor out there, right? So even if you do the best you can with the chemistry, you're not going to get there, which means that you need to develop materials, right? You need to develop materials to also sustain corrosion. And then you look at all the corrosion tests that people have done out there in the literature. Well, here is a plot that shows all the mass loss because you dissolve your material in there as a function of time, and you see this is all over. So many different data everywhere. You can't really, make anything out of this, right? So that's a bit of a problem because that means that you have a lot of mice in the house, right? You have lots of issues here. Some of them, are relatively obvious. In this plot, there is, the temperature is not always the same. There is some variations, but not a lot. And then there is a lot of other parameters, salt purity, and so on. One thing that you can see in this plot is usually impure salt. So the field, the symbols are usually a higher weight loss than pure salt. So really purity of the salt also matters. And to that extent, here I'm showing you a plot, some figures of a purification system we have at UW Madison that allows you to purify salt. So it's for fluoride salt in this case, but you could do the same kind of things with chloride, and just maybe you change your chlorinated or fluorinated agents. But for fluorine, we use HFH2. mixture to a kind of, first of all, HF is gonna, all the oxides, particles in your salt, if you put HF in there, they're gonna be fluoride, right? The oxides are gonna decompose to fluoride. And then it's a question of reducing those fluorides. And so you bubble H2 to reduce those fluorides to metal, and then you just have to sieve the salt to remove those metal particles, basically, that have very low solubility in the salt. So that works pretty well. Here's an example. You work in glove box because salt love water or oxygen, so you don't want any oxygen and water ingress in your environment, because otherwise it's going to get very mushy and viscous and so on, so you don't want that. But what you see here is basically a 600 degrees Celsius water type of thing, right? It looks like water, but it's very hot, and it behaves like water. It's in terms of heat capacities and all that. It's relatively close, and so it's super interesting for thermohydraulics to have some fluid that is like water but at 600 degrees Celsius and above. So that's how you retrieve your salt from the purification vessel in a glove box. And why I say it's so we have more data now on this, and we have a paper in preparation to show this kind of effect of purification on corrosion kinetics. But 316 stainless steel, approximately 50, a factor of 2 lower weight loss when you're working on a purified salt, right? So really, purification of salt is very, very important. The main, as we found out, and I don't have the data here, the main impurity that is driving corrosion in this case are oxygen-bearing impurities, mostly moisture that could create, for instance, HF in your salt is one of the responsible. So how does that look like? Well, solution of chromium from the grain boundaries. It's a well-known effect. Chromium fluoride is very stable, like chromium oxide, right? But it dissolves, of course, in the salt. So you have this dissolution path. You're losing your chromium from the grain and the grain boundaries, and you see those weakening of the grain boundaries because of that. So that's a well-known observation of chromium-bearing materials in molten salts. Other things that we've looked at a little bit that are of interest, I wanted just to share that briefly with you, is the fact that we looked at galvanic corrosion. So if we put very noble elements and we put a 316 stainless steel capsule around it, and we have electrical contact between them in the same media, we would expect the 316 stainless steel to be severely oxidized, and the coupon of nickel, copper, and moly to be very well protected against corrosion. And if we put an insulator here, we would expect then this galvanic corrosion to not occur. So this is the kind of test we do. This is in a glove box. We have a well, we have a furnace around the well, and then we take those capsules out of the glove box. So here you can see the nitride caps that are preventing electrical contact, and then we have those stainless steel cap that remains electrically connected, right? So we take those samples out. It's I forgot to remove that one from Bruce Willis, but anyway, it's very hot in there, so you got to know what you're doing, and that's about 700 degrees Celsius. You got to work with here, and we are the salt is still liquid, and we are retrieving the salt to kind of get this chemistry of the salt using ICP-MS afterwards. You see the salt a little blue here. There are corrosion products into it, and so on. So this is typically the type of test we do, and then we weigh the sample. We clean it up, and then we weigh to see how much materials it has lost. And then, surprised with the experiment, we see an increase of the mass. We don't see a loss, right? So that was a little surprising to us, especially nickel, that is supposed to be pretty inert, has gained quite a bit of mass in this experiment. And clearly, this is not something you would expect from galvanic corrosion, right? And when you look at direct contact, so the DC is direct contact, the BN is this boron nitride insulation, you don't see a difference, right? Very little difference when you use nickel, copper, or moly. TZM is kind of 99% moly. You don't see a difference between electrical contact and not electrical contact, and in most cases you see weight gain. So what is going on? Well, I'm not gonna go into the detail of that. I invite you to read those papers at the bottom, but basically what happens is that you have we think galvanic corrosion has no effect. It's not something that is important at those high temperature. We think on the other end that there is activity gradients between the stainless steel and the samples. And so you have a dissolution of the elements from the stainless steel in the salt, as expected. But those elements can then enter the material here if they have an activity in this material that is low enough, like chromium in nickel. There is quite a bit of solubility of chromium into nickel and iron. And so relative to 316 stainless steel. And so basically chromium is just being pumped by the nickel and ended up in the nickel, which leads to weight gain of those of that nickel. So these are just a few experiments to show you what you have to be careful about and so on. And maybe I've told that to some of you already, but I would really encourage everyone to detail as much as possible all their experimental setup when they work with molten salt. Volume of salt, purity of the salt as much as you can, surface area of your sample, capsule being used, temperature, and so on. This is very important to report that for the community. But yeah, so those experiments, they took a PhD, right? PhD student, Cody Falconer, who's now working at TerraPower, is an excellent PhD student, but it took him probably 4 or 5 years to do that purification and get those nice experiments being done and some modeling. It takes a lot of time, and that's the problem is we don't have time, right? As I mentioned. So here's an example. It's a plot I put together a few years ago where you see the development of materials for aerospace industry, like the turbine engines, and the nuclear industry. Since approximately World War II, you see that the aerospace industry has developed the materials about 5 degrees Celsius per year, and we're about half that pace for the nuclear industry. So really, we're a little behind, and about 50% of the pace of the aerospace industry. So we need to do better than that if we want to decarbonize that electricity around the world. And for this, one of the things I started to look at a few years ago is the high-throughput data collection and analysis. So how can we accelerate the corrosion test? Well, so we came up with this framework, which is, okay, I don't need to only accelerate the test. I also need to accelerate the processing of the alloy. I need to accelerate the test. I need to accelerate the data collection. And then I can use potentially some machine learning or artificial intelligence tool to kind of tell me, okay, looking at all the data that you have gathered, Adrian, here is what you should look at, right? So this is this kind of interesting framework that I will detail from now on in this talk. And we're going to start with the alloy processing. So we are producing alloy using additive manufacturing because it's a very fast approach to produce metal parts of relatively well-controlled composition, relative to arc melting that can be relatively fast, but it's very labor intensive and also not as fast, of course, as additive manufacturing. So here is how we process, sorry. So we have this chromium, iron, manganese, nickel. So those are powder hoppers of single elements. We are, of course, looking at other powders, refractories, and so on more lately, but this is more like a case study to look at stainless steel-like elements, those 3D transition metals. And here is an example of how that works. So we use those powder hoppers. We flow the powders in our system, and we flow argon to carry the powder of a given composition. And then we blow the powder with nozzles in the focal point of a laser. The part then melts, right? And then we move the focal point for the parts to solidify, and we can melt above it, right? So we create this kind of part on a build plate. So that works quite nicely, as you probably know. I mean, additive manufacturing is now a common thing out there. And we can, for instance, print small squares or small cubes like that. One of the issues we can have is this, we don't necessarily melt everything because some powders have a higher melting point than others. So we tend to reglaze, as we say, or remelt using just a laser with no powder so that everything is melted. And then we do that again and again and again, and we develop, and you build a few millimeters of a cube like that of a given composition, and you don't change the composition. And you end up with those plates. We call them Lego plates, where you have a build plate and you have your material on top. And then what's cool about this is that you can really, work on it on the plate, right? You have 25 alloys on your plate. You can homogenize them, polish them, test them if you want, all of that on the same plate. So this can go quite fast. And so we put those plates in about 24 hours at 1,000 degrees Celsius to remove solidification structure from additive manufacturing, and then we thermal age them at 700 degrees Celsius to stabilize the microstructure at relatively high temperature for 24 hours. So then we use CalFAT to kind of check, okay, what is the expected crystal structure out there? And we can also do XRD to check if those crystal structures are indeed the one we observe. So we have about 150 alloys we've produced in this tetrahedra here, and most of them are in the single phase with high nickel content, and because they are more printable and also high iron content. You don't see much toward high chromium and high manganese because those parts don't print very well, right? But we have a single phase and also dual phase when you get closer to the chromium-rich area. So here is the kind of the look of the plate once it's been polished. You see some micro porosity. It's there, right? You can't. I mean, it's difficult to avoid, but it's below about 0.1%. We've quantified it, so it's really minimal, and it's not at a level that will actually impact your corrosion test significantly in molten salts. So we're not really worried about this. So then we check the composition with X-ray fluorescence. We have an X-ray fluorescence gun that we can use to measure composition relatively quickly to see how close it is from the target composition. Clearly, it's not very close, but we don't really care because we just want to populate the tetrahedra. We're not really looking at, I want this alloy with this composition, right? It's more, the idea here is to populate the overall tetrahedra. We can use automated XRD to check the crystal structure. As I mentioned before, then we check relative to the predicted CalFAT-based databases. And then we can also do SEM and EBSD to look at the crystal structure and the SEM-EDS. One of the issue we have here with the crystal structure is you can see it's not really recrystallized. And that's one of the thing we have to do a better job is the heat treatment of our additively manufactured part, especially when we go to refractories. And we are just building a new furnace for this that can go to much higher temperature and can accommodate many samples, about 25 samples. So we can get a better recrystallized microstructure of our additively manufactured parts. So something to keep in mind. Okay, so that's the production of the materials. Now I want to talk about the testing itself. So we use droplet tests. So those droplets, it's relatively simple. We made this kind of punch tool and pressing tool to kind of create a little, piece of chunk of salt that are always the same mass. They look like a drug pill a little bit. And then we kind of weigh them just to make sure that they have all the same mass and so on, and we can store them like that. So we have a heat plate in our glove box, and so we can put those droplets, those solid chunk of salt on top of our alloy. We close our heat plate, we heat it up to 500 degrees Celsius for about 100 hours, and then at the end we open the heat plate, and this is what we obtain when the test works, right? So here is a beautiful case where the test has worked, where you see the droplet has remained on the sample very nicely, and you see some corrosion products that have built up. You can remove the salt, store it for analysis, and then you can clean up the surface and look at it after corrosion for each one of your alloy. And this is before corrosion. So you see some polishing marks, right? And again, because we polish everything together, so the polishing is not the best. But again, it's high-throughput technique, so you're not going to get the super nice colloidal silicate that you would get if you were to polish, one or two samples together. But here you do 25 samples together, right? So it's a different. You got to decide a little bit about, if you want to go quick and it's not going to be as nice, or very, very precise high fidelity, but it's going to take a while. And I guess we should do both, right? It's important to do both sides. But then after corrosion, you see this kind of feature that appears at the surface of the alloy. And if you look closely, you see very interesting patterns, right? So you have various patterns that are, of course, related to crystallography, but not only, right? I mean, if you look at the scale of this is way smaller than the grain size. And so we are wondering a little bit, okay, what is actually leading to those interesting features that you observe, faceted versus maybe more ligament type of morphology. So we use two different metrics of corrosion resistance. How do you characterize now corrosion resistance? We used what's called glow discharge optical emission spectroscopy. So we have one in the lab that allows us to really obtain depletion depths. So on the left here is your surface, and then you can get the concentration as function of depth using this method. It's a very quick and powerful method to get very accurate values of your elements. And you see the depletion, for instance, of manganese for this alloy here, and you see the depletion of iron and manganese for this alloy here. So then you can look at the depletion depths, but that's, you get a lot of data like that, right? So at the bottom is the composition of your alloy. So yellow is nickel, red is manganese, then you have iron, red. So all of your alloy composition at the bottom, and on the top is what is the depletion depth. And the issue with this method is that you can have an alloy that has a very small amount of element, but a very high depletion depth of this element, right? And at the end, not much then will be dissolved in the salt, even though you have a very high depletion depth. So this matrix of corrosion was not working very well for us, even though you were learning interesting things. It was not a very good one to transcribe for machine learning application. So we decided to use on the opposite, we use the ICP-MS of the salt to look at the corrosion products in the salt. And this is more like a holistic, general corrosion quantity that you can work with. And you see how you have all the ppm of elements in the salt for all those. This is about 82 tests. And those tests are the one we've used for training the machine learning algorithm, which I'm going to talk about it right there. So the idea of the machine learning algorithm, what we use is a random forest regressor. So we need to featureize our alloys. So we have a lot of different features, activity of elements within the alloy and so on and so on and so on. And then we have our output, which is corrosion products in the salt in terms of concentration from ICP-MS. So again, this is all the features we've used. I won't go through them in details, but I think there was about 75 different features that we were able to extract from databases, from characterization, to really describe our specific sample as much as possible. And so each sample will be slightly different from one another. And the variable of interest are this alloying element in the salt. All right, so we trained our machine learning algorithm using what's called a 5-fold cross-validation technique in the random forest regressor. So basically, what that means is that you're going to train your machine learning on 20% of the data, and it's going to test on the 80 remaining percent, and so on. You're always going to train on different set of data, and at the end, it gets all the results together, and you can get the mean absolute error from your random forest regressor model. And we have an error of about 74%, which means, if I give this machine learning algorithm an alloy, it should be capable to give me at 74% precision the corrosion after 96 hours in that salt at this temperature. Most of our samples are below 50%, which is good, right? We don't have a lot of outliers, so that's a good sign. And since we had more tests, we had about 110 tests that worked pretty well, 110 alloys that worked pretty well. We were able to look at, to add 22 alloys from that the machine learning has never seen, right? It's never been trained on it, not part of the 5-fold cross-validation. Then those 20% were relatively well predicted, as you can see from this plot. Most of them were below 50% for sure error. And then if you add those 22 alloys to the 88 alloys that we have done before, you also can reduce the error, right, of your machine learning algorithm down to about 58%. And when we did repeat tests of the same test to look at the experimental error of our results, and it's about 15% or 14%. So, we think that as you add more and more and more, and we're working on that, you can get down to 15% error. I'll pass on this one here, but just now you can actually use the machine learning algorithm to predict corrosion of elements of alloys that you don't that you have not tested. So here is an corrosion magnitude in terms of corrosion products in the salt that the random forest regressor is predicting. And not surprisingly, but that's a good thing, you see the higher manganese and the higher chromium tends to corrode more or predict to be corroded more. And on top here, you see this is the Astelloy N, which is a nickel-based alloy that has been developed for molten salt. I mean, it's a projection of Astelloy N because there is more than just those 4 elements. And then stainless steel 316 is down there. And the idea is, can I find, for instance, alloys that are behaving better than stainless steel 316? So you see that the alloys that are behaving much better than 316 stainless steel are here in blue. 2 standard deviation better than this 316, and they're very low manganese, so we can almost consider them as a plane. So we have projected them on our ternary diagram, and you see that these elements here are predicted to be better than stainless steel. And it's interesting to see that some of them have relatively high chromium content. So it's not, chromium content itself is not a good descriptor of your propensity for corrosion. High nickel, relatively high chromium may actually behave way better than stainless steel. All right, so one other thing that you can do with molten salt, with machine learning is not only prediction, but interpretation. What's good with random forest, that's not a black box. Random forest regressor, you can actually interpret the results. It's not maybe the most powerful machine learning algorithm out there, but it's interpretable. So for that, first of all, we need to reduce the number of features. We have 75 features. That's too much. Some of them are collinear to one another. They're monotonically interdependent. Like for instance, activity and concentration. They're related physically to one another. So we need to reduce the number of features. For that, we use a technique called Spearman pruning that allows us to see which features are relatively they follow the same monotonic behavior. So then we can regroup them together into one feature. So in other words, what we do is we orthogonalize the matrix of features. So we have the most non-dependent features as possible in our matrix for our machine learning. So with this, we can go from 75 to 18 features using Spearman pruning, and we only increase our error by, from 56 to 64%. So we lose very, very little accuracy by reducing the number of features by a lot. And all the features are shown here at the bottom. I won't go into the detail of those right away, but there are about 18 features that we have kept here. So what do we do with those features? There are 2 main plots that we put together, which are plots that you don't see out there a lot, but I think they're actually quite interesting to look at the results. This one is relatively simple. It's to look at the distribution of the feature. So you start from the most important feature, I'll come back on that, is this diffusion of nickel. And then the least important feature of those 18 features is then you do clockwise and you arrive at the manganese diffusion on the nickel sublattice. And so the idea here is that you want to make sure that each feature is well distributed among its population, so that you don't every single alloy doesn't have the same value of these features. And so most of them behave very well. You see that, for instance, our iron over manganese ratio is a little clustered here, but overall they're relatively well distributed in terms of values in our alloy population. And this is here's the most important plot that shows you the importance of each feature. So when a feature value is high, it's red. And when a feature value is low, it's blue. And then if corrosion is high, then it's going to be at the exterior of this graph. And if the corrosion is low, it's going to be at the interior of this graph. So what is this? First of all, if you look at the activity of chromium down there, you see that when the activity of chromium is high, so it's red, you have an increase of corrosion. And that's, again, we expected that. When the surface energy is high, again, corrosion rate goes up. If the coefficient of chromium is high, you tend to also have an increase of corrosion rate. That, again, was expected. When you have a high electronegativity of the material, then it means that it's very different. It's very close from the electronegativity of the anions, and so you have a lower corrosion rate. So you have less of a driving force in this case. And when you have a high work function, again, it's very difficult to extract the electron for the corrosion to occur, so you have a low corrosion rate. But what's very interesting that the most important feature of all is this diffusion of nickel that we didn't expect. Really, we didn't expect that if you increase diffusion coefficient of nickel, then the corrosion rate will increase because nickel is supposed to be noble. So we're trying to understand this. We think that there is relation to surface diffusion, for instance. So we looked at the facets or the morphology of the surface, and we noticed that for low nickel diffusion, we tend to have more faceted features. For high nickel diffusion, we tend to see those more ligament morphology. So potentially, the nickel diffusion is playing a role on the morphology of the surface that then is connected to the corrosion rate of the alloy. All right, so just to finish, just to show you kind of the overall, progress here. This is a paper we published in Matter, so I will invite you to look at this. It's open access. And just 3 more slides to kind of go beyond this about what we're doing. The truth is not all the tests are very successful. We have also tests that fail tremendously and terribly when the droplet basically just spills and disappear. And that happens a lot when we're working on nickel-rich elements, especially nickel binary chrome. And we think that that's because it's very wettable. There is a good wettability, and then the droplet spills like that. So we want to make a more robust corrosion test for these high-throughput experiments. So we tested a few things, for instance, we look at putting some boundaries here made of quartz around the sample, and then put some boron nitride paste to kind of prevent the salt from spilling. Here is an example of, that you can see one of those droplets melting inside of that quartz with an alloy on top, the bottom, sorry. And you see the boron nitride paste on the side. It looks pretty good up to a point where it's actually going to leak. Unfortunately, after about 4, 5, 6 hours, we often see that boron nitride paste deteriorate, and you're losing the salt. This is the work we are actually doing with the CEA in France at the moment, and you see that kind of very interesting behavior where right there the salt just went out of the quartz, and now it's gone basically. And so we are trying to use a better experiment where we are maybe now using a cap and a better seal to prevent the salt from spilling. Another thing we're doing is we're trying to develop additively manufactured materials for refractory alloys. So we are developing a new machine, completely new machine for additive manufacturing that is able to print, tungsten, molybdenum, tantalum alloys in small cubes like that. And so this is a piece. This is the additive manufactured machine that has been built. And it's done by a colleague of mine in mechanical engineering, with which we work with. And so, this is a very exciting new approach to obtain refractory high entropy alloys, for instance, for our research. And the last slide here is we're also looking at doing machine learning on the facets, or on the morphology of the surface. So, for instance, we can use computer vision aided software, right, that are machine learning based, for that matter, to kind of extract the porosity on these images. And that helps us to get more descriptors, more features, right? So we have much more features than just the 75s I talked to you about. We have now more than 250 features. So we can really enrich our machine learning random forest regressor. And so we also then want to use Spearman correlation pruning, and at the end arrive to, maybe using the morphology of the images afterwards to better inform if it's related to the corrosion rate, as I mentioned earlier. Right, so I'll stop here, and I thank you for your attention. And of course, we have time for questions, so feel free to ask any question you want. Thank you.
Thank you very much. It was very interesting. I think I've seen for the very first time liquid salt actually, like on your video. So
Stephen, you can melt some salt in your pot in the kitchen. That works too.
But I never did so far. Okay, so I don't see any questions in the Q&A or chat yet, but please, you can either enter them there right now, or you can also raise your hand, and then I can let you speak. I think that should work. Yes, one moment. Now you should be able to speak.
Yes, do you hear me?
Yes.
Okay, thank you. Thank you for your nice presentation and the nice work you presented. So I was wondering on slide 10, or pretty much towards the beginning, if I'm not making a mistake, with that delta, with that delta G diagram that you are showing for different metal fluorides forming.
Yeah.
Because afterwards you mentioned also impurity oxygen and HF in your system, but with that diagram, are we considering that F2 is your oxidizing agent, or is just a way to consider the affinities of different metal fluorides being formed?
Yeah, so no, it's a very good question, right? You're right that in this Ellingham diagram plot that I'm putting here, we are, of course, considering that the half cell reaction is F2F minus, right? That's the way you would do it. On the other end, I've just mentioned as well, and I'm glad you paid attention, that the impurities are actually responsible for corrosion. So it's not the F2, F minus that are necessarily, this agent is not really responsible for the oxidizing reaction. But what's important though is that those impurities that I've mentioned about, what they're mostly going to do is change the redox of your salt, right? Relative to the F2, F minus reaction. And so the redox of your salt at the end of the day is going to be what's your metric or your probe to see how much oxidizing is your salt. And you don't really, I mean, I shouldn't say that maybe. It's not that you don't really care, but you at this level, I would say, you don't really care necessarily what is the oxidizing agent. You just want to know where is your redox potential of your salt, and whether it's impurities or maybe some intrinsic property of the salt that is making it oxidizing. You don't really care at this point, right? You just want a redox that is relatively reducing towards your element. And in that case, using Ellingham diagram is very powerful, right?
You are, you want to avoid that in any way, but with HF and with the purification that you're using, you're that is intended to reduce F2. So if you're considering oxygen or HF, then the story is different. I mean, you're producing metal fluorides, you're trying to remove HF and with producing metal fluorides anyhow, but with oxygen, it would be a different story, right?
If we were to put oxygen in there, you mean?
Yeah, I mean, if you have impurity oxygen that you are not going to remove with the purification method you have right now.
Oh, we are actually. If you have like oxides, for instance, if you consider chromium 203, if you bubble HF, you will end up with chromium fluoride and water, right? And the water is going to bubble out. So you just remain with your chromium fluoride afterwards. So it's a way to remove the oxides, or that are usually very stable in salts. You can remove them by putting this very strong fluorinating agent, which is HF. So that's one way to remove that. To remove moisture, just itself, I think we have a good method is just to bubble argon, right? Usually it works pretty well. We've done that as well, just bubbling argon. It also reduces the corrosion rate, not as high of a reduction when you do HFH2, but it gets your corrosion rate pretty low, and we see the oxygen species also getting lower in the salt. So bubbling argon, bubbling H2 is very good at removing, we think, most of the dissolved gas species, moisture, and dissolved oxygen in your salt. And then if you want to really break the oxides and remove them, then you need to have the HF in there.
But with this diagram, I mean, basically most of the metal fluorides are stable, right?
With this diagram, I'm only looking at the metal fluoride. So you're right. If you want to look then at the oxide versus fluorides, you need to look at those oxo-acidity diagram, where, of course, at a relatively high partial pressure of oxygen, you will stabilize the oxide versus the fluoride. That's for sure. But we try, at least in molten salt reactor, we try not to work in very very low oxoacidity systems where the oxygen partial pressure will be relatively high, mostly because then it's very difficult to control the redox. You now have multiple oxidizing agents. You have the oxygen, you have the fluorine. And I think controlling the redox in this case is very, very tricky, much more complex. People working in thermal energy storage, when they have those significant large tanks, of salt, maybe in this case, it's too expensive to use inert atmosphere, and you may want to work in the air. And in that case, you're going to have oxygen in your salt, and that's a different story, right? But in this case, yeah, you should look at oxoacidity diagrams to look at this difference between oxide stability versus chloride or fluoride stability.
No, I mean, if you have oxygen, definitely it will take over in the end. Yeah. Thank you.
Yeah, of course. Yeah.
Thank you so much.
Okay, thank you. In the meantime, we have some questions in the Q&A from Emmanuel Herms. Thank you very much for the very smart presentation. Just a small remark. Why not manufacture by additive manufacturing small crucibles, small cup, to prevent flow of the droplets instead of plates?
Yeah, that's an excellent question. So the idea, you could, since with additive manufacturing, you have some freedom in the geometry of what you want to print, we could actually print small crucibles and the droplet won't spill. The issue with that, though, there are two main problems. The first one is it's very difficult to prepare the surface of the material, right? Because if you have the crucible now, you don't really have access nicely at the surface to polish it using standard auto polishing procedure. You can use other type of procedure, but they are not as well developed as just the regular colloidal silica, diamond paste, and so on. So it's a little difficult to have a very nice surface polishing. And then also it's a little tricky to control the surface area very well because you want the same surface area to react. And using, for instance, we couldn't have used GDOES in this case, right? Because now you don't have like a planar surface. So the GDOES, we couldn't have used it. ICP-MS, most likely we could have been able to use that. So it's a possibility, but it's not as simple as it seems, and at the end may create more hurdle than we would like, right? So we looked into that. We decided to not go in this direction, but it's certainly something that people could look into if they have the means and capabilities. Yeah.
Thank you. Then we have another question from Xiang Yu. Thank you so much for the presentation. Very nice work. I have a question about the corrosion tests with molten salt drop. How do you control the oxygen content and moisture during the tests?
Yeah, well, I mean, we don't control it, right? So we're in a glove box. So the glove box, of course, has oxygen and moisture sensors, which are at very low level during the entirety of the test. But we don't measure this oxygen and moisture in each droplet, right? We do measure oxygen and moisture in the base salt using, for fluoride salt, we can use inert gas fusion, using a mass spectrometer. For chloride salt, the techniques are a little different. You're looking at conductivity of the gas, but we have colleagues that are doing that for us, and so we can measure in the base salt. Before and after corrosion if we want to, but we don't control it per se during the test, only by working on an inert glove box.
Okay, thank you. Are there any other questions? You can raise your hand or no. Yes, from Laure Martinelli from CA. Thank you very much for your nice presentation. I think it is quite complex to make a link between the diffusion coefficient of nickel and the shape of the alloy salt corrosion surface. Do you have currently an idea of the effect of this diffusion coefficient on the shape of the surface?
Yeah, so you're right. It's very complicated. It's not something very easily from back of the envelope calculation you can do, right? So there is one research group at the University of California, Berkeley, from Professor Mark Asta, ESTA. They do, and it's in collaboration with Los Alamos National Lab with Laurent Capolungo. And they do phase field modeling of the corrosion to look at how the surface morphology evolves when you have molten salt corrosion. And it's indeed quite complex, but what's cool about phase field is that you can turn some knobs a little bit and see which parameters influence the surface morphology. And they do observe that the diffusion coefficient of nickel has a strong impact on the morphology of the surface. And you have a redistribution of elements, chromium and nickel, due to those diffusion coefficients. So I don't have a short answer for you, but I will invite you. They've published 2-3 papers out there recently on this topic of phase field modeling and surface morphology, and that is I think the path that one should take if you want to get this correlation properly between diffusion coefficient and surface features.
Okay, thank you. I see no further hands raised or no further questions. So your last chance. If not, then I would like to thank you one more time for giving this very interesting talk. And with this, I think we are at the end. So I remind you on the Working Party 4 website, please pass by from time to time. If any questions, send an email to me or to my vice chair, Laura Martinelli at CA, and hopefully many of you we will meet in Stavanger at the nuclear corrosion session. And until then, have a very nice summer and summer holiday time, hopefully vacations. And yeah, at probably next year around spring or early summertime, we will have another such webinar. But first now, Eurocore. Okay, thank you very much and goodbye, everyone.
Thank you again. Thanks, everyone. Bye-bye.